Welcome to Pod 4 Journal Club. Today, we're diving into a paper that asks a really mind-bending question. What if we could solve our biggest data problems with a computer that's a million times smaller than what we use today? Let's break down how quantum computing could actually make that happen.
So, to really get why this research is such a potential game changer, we have to start with a huge problem that's quietly brewing behind almost everything we do. Every click, every photo, every single thing we do online is adding to this mountain of data that's growing way, way faster than we can deal with it. So, are our computers about to hit a fundamental wall?
We are creating an absolute avalanche of data every single day. And it's not just cat videos and social media posts. We're talking about critical scientific data, from decoding genomes to mapping the stars. And for the computers we rely on today, all of this information is becoming a massive, massive headache.
This bottleneck actually has a name. It's called the memory wall. And it's a really deep problem for our classical computers. Basically, we're getting exponentially better at making data, but our ability to actually process and learn from it just isn't keeping pace. The gap is getting wider every day.
So far our solution has pretty much been to just go bigger, building these absolutely enormous, power-hungry data centers. But this new research asks a much cooler question. What if, instead of building bigger, we could build smarter? What if a totally different kind of computer could just sidestep the problem entirely?
And this is where things get really, really clever. See, the new algorithm these researchers have come up with doesn't try to just brute force the problem. Instead, it acts more like a brilliant artist who can create a perfect, detailed sketch of a massive landscape by just taking quick glances, without ever needing to see the whole thing at once.
The technique is called quantum oracle sketching, and the core idea is, well, it's pretty wild. It lets a small quantum computer build an incredibly accurate model of a huge data set, a model you can ask questions of without ever actually saving all that data. It just looks at these tiny little samples, one at a time, on the fly.
So here's how it works, conceptually. A quantum computer takes a quick peek at just one piece of data. It uses that information to make a tiny, tiny adjustment to its own quantum state, like a little nudge. And then, and this is the absolute key, it immediately throws that data away. It's gone. It just repeats this process over and over and over, and by doing this, it builds a complete, super accurate picture of the entire data set.
Okay, so that's the how. But the real question is, what does this new method actually get us? Well, this is where it gets really exciting. The results that the paper lays out, they're not just a small step forward, they are absolutely staggering.
The simulations in the paper show that you could potentially reduce the size of the machine you need by 6 orders of magnitude. Now, to put that into perspective, that's 1,000,000 times smaller. It's like shrinking a giant data center down to the size of a laptop. And get this. This incredible efficiency is achieved with a surprisingly small quantum machine. The simulations suggest this is possible with fewer than 60 logical qubits. And a logical qubit, just for context, is basically a stable, error-corrected quantum bit, the real workhorse of a future quantum computer.
This slide really just nails the difference. Think of it this way. If your data set gets twice as big, a classical computer might need to get 4 or even 8 times bigger to keep up. That's exponential growth. But with this quantum method, the computer only needs to get a tiny bit bigger. That's logarithmic scaling. It's a completely different and way, way more efficient way of handling growth.
And hey, this isn't just some abstract theory. The researchers actually tested this out by running simulations on real-world data. They looked at classifying the sentiment of thousands of movie reviews and at analyzing complex single-cell RNA sequencing data. And in both of these very different, very real-world cases, the quantum advantage held up.
An advantage like this could unlock a huge range of tasks that are just fundamental to modern science and AI. We're talking about solving massive systems of equations, classifying data on a scale we can't even imagine right now, and finding those tiny hidden patterns in super complex information. This is basically the engine of discovery.
Okay, but it's really important that we keep our feet on the ground here. This sounds amazing, almost too good to be true. So, what are the challenges? What are the limitations that the authors themselves point out in the paper?
So the biggest hurdle by far, right now this is all a theoretical breakthrough that's been backed up by computer simulations. The next giant leap is to actually build the physical hardware that can do this. The physics seems totally solid. The theory works as long as quantum mechanics itself is correct. The real challenge is now an engineering one. Can we actually build the machine?
But this is where the paper takes a turn, into something way more profound.
This research has an implication that goes far beyond just building faster computers. It actually touches on the very foundations of physics itself.
The authors make this incredibly powerful claim. They say that if we can build a machine that actually does this, it won't just be an amazing piece of engineering, it would serve as a fundamental test of quantum mechanics itself, pushing the theory into a new realm of complexity we've never been able to explore before.
Think of it like this. For decades, famous experiments have tested the really weird parts of quantum theory, like that spooky action at a distance that famously bothered Einstein. Well, this research proposes a whole new kind of test. By using big data, we could actually probe whether the strange, exponentially huge reality described by quantum mechanics is, physically real.
And that leaves us with a truly provocative thought. We started with a pretty practical problem, right? Our computers are hitting a wall. But this research suggests the solution could lead us somewhere truly incredible. The path to understanding the fundamental nature of our universe might just run straight through the heart of our biggest data problems. So could big data be the key that unlocks the universe's deepest secrets? Let us know what you think. And if you enjoyed this breakdown, make sure to subscribe to Pod4 Journal Club.